Here we are once again. It's the Physics 105B video lecture. Physics 105B video lecture 4. And today we're going to get into the Lagrangian mechanics. Finally, we've been studying the variational calculus. So variational calculus is what we have been doing. And I had derived everything we need to take it right over to mechanics. So what I'll do here is just write on the left side of the board, I'll write down what we've obtained. We have the idea that if we have a function y1, yn, y1 prime to yn prime, and x dx. So if the variation of this thing is 0, and what that means is the unknown functions y and y prime of x, 1 through n, when plugged into this integral, will give a value. There is a set of such functions that give a minimum value. Okay. So for such a set of functions that under this criterion here give a minimum value, those are the y sub 1 to y sub n prime of x. So what follows from this is that we have the Euler-Lagrange equations, d dx, df, dy sub I prime, partial f, partial y sub I equals 0, I equals 1 to n. Very important that these different functions be independent of each other. That was part of the condition in order to obtain this form for all of those equations. And we have one more condition here, and I'll just write down sum over partial f partial y sub I prime times y sub I prime minus the function f is equal to a constant, comma, if f is not explicitly a function of x, of that variable there. So we can use this on maximum and minimum problems. We can find the shortest curve connecting 2 points in the plane, in space, on a helix, on the surface of a globe. We can find the curve of shortest time. We can do all kinds of interesting problems here. We use this principle, we can minimize the potential energy of a hanging chain and find out that it takes on the shape of the catenary. Okay. So it's a great mathematical subject on its own. Now in physics, it plays a huge role as well. So in physics, and say in mechanics, since that's what we're studying, there's something called the principle of least action. And that is a variational principle. Principle of least action. Hamilton's principle, you hear different versions of this. And that is the following. I'll just formulate it. For L equals T minus U equals, and okay, 1/2 sum M sub I R sub I dot squared minus the potential energy R1 to Rn. Right, we were working with the energy, which was the sum of these two. Here the Lagrangian is the difference of the kinetic and the potential energies. Okay, so we've just been studying how to form expressions like this, okay, when we're doing many particle systems. So we have this thing called the Lagrangian, L called the Lagrangian. We have a principle, namely variation of L dt t1 to t2 is equal to 0. And what that's saying is that the motion of the system that minimizes this expression here, or actually I should put it this way, the true motion of the system, the motion that the system takes on under the laws of nature, minimizes this integral L dt, and there's this variational principle. So since we have this expression in complete analogy to this one, we can just inherit the equations of motion. And what I'm going to show you is that they are Newton's laws, and then you'll be convinced, right? If you see Newton's laws come out of this, then you're going to be convinced. At least that's my argument for now. Okay, so this is the principle of least action. L's Lagrangian integral L dt is called the action. Okay. The action has the dimensions of an energy times a time. Okay, we'll talk more about that later. So yeah, the principle of least action is stated right here. And it means something to us because we've studied this variational calculus. So let's draw the conclusions. Okay, so we have R sub I t, R sub I dot of t, I equals 1 to n. Suppose we have n particles, 3n degrees of freedom. So are the solutions, or are the actual motion slash trajectory of the system okay, then the action takes on a minimum and we have the Euler-Lagrange equations. So D, and the translation should be apparent here, and we'll point it out. Let's just write this down. D dt partial L with respect to R sub I dot minus partial L with respect to R sub I is equal to 0, I equals 1 to n. So what I have here, these are 3 equations at a time, right? So if I do a partial with respect to the vector, that's a gradient, as we've been doing before. We called it gradients of I recently. And this is the partial of Lagrangian with respect to R sub I dot, so those are also 3 derivatives. Okay. But yeah, that's the form of the Euler-Lagrange equation. And the next thing to do is actually do this, do the calculation. So calculating, we have L is up there, so let's just do it piece by piece. We got D, L, D, R, sub I dot, out of that whole sum. Well, let's use a different subscript. Since we have I in the sum, we have to use K, and that's going to be the M sub K, and then we've got the 1/2 from the 1/2 there, and then the 2 R sub I dot. Okay. And then we have the D, L, D, R sub K. And then in this particular Lagrange, we only have the coordinate right here, so that would be minus du d r gradient. And now you can see with the 2's canceling, I take the complete time derivative of this. I have m sub k r sub k second derivative minus the negative, so plus du d r sub k equals 0. That's just Newton's law, okay? Or m sub k r sub k acceleration equals minus du dr sub k, so that's f sub k. K equals 1 to n, because we have all of those equations. Check that off right there. So that's Newton's law. How about another color? So this variational principle gives us Newton's law, and that's the condenser, so to speak. It is possible to derive this principle. I just did it with the Physics 203, starting with the systems of point mechanics, but it takes some more time. We'll save that for another class. Because then you can derive this, and then of course you apply it here. And you could also say, well, the next thing you can say is, if that's all we get, then why do we even go there? Because we were studying point systems. But this is just the condenser, and we're going to be able to do many other things with this formulation. Okay. For systems with many degrees of freedom, you really have to go into the Lagrangian formulation to get anything done. Okay, so yeah, it's going to be great. And this was just to convince everybody that we have Newton's law coming out of this principle of least action, the variational principle. Okay. You know, since we have this thing here, I'll go ahead and deal with this right away as well, before we launch into the whole formal development. Because yeah, we inherited the Euler-Lagrange equations because we had the exact same form here. Make sure, by the way, you do this translation between here and here so you really see what's going on. Okay, this is positions, velocities, and time. Okay, so these are my r's and my r dots, r primes, and this is the time parameter when we take it over to here. Okay. Yeah. So I do want to address the meaning of this. See, this was this interesting combination of things as constant. So we just said, okay, that's a first integral, but it didn't really carry any meaning for us. On the other hand, if you're solving a problem and you can make use of this, then you do, because it's reducing the order of your differential equation. The Euler-Lagrange equations are second order, and this equation right here is first order. So if we want to form this thing here, so we're following with this thing. So next, the conserved quantity. Star. So I'll just call this thing star right here. Okay. Conserved quantity star. We're going to do the translation again. So remember, this was derivative y prime. So here it would be translated as partial L partial R sub I prime, no, dot, sorry, dot product with R sub I dot minus L. So this is I equals 1 to n. And this scalar product is 3 of these each time, okay? The x, y, z of the position, of the individual position vector there, equals a constant. So then we have to say, well, what is this? And we have our Lagrangian up there. No, we don't. Let's go ahead and write it out. L equals 1/2 m sub I r sub dot squared minus u of r 1 r n. Okay. Yes, so we have dl, we're going to use the letter j or something, so partial L, partial r sub j dot is equal to m sub j, r sub j dot. Then that sum is going to be dl dr sub j dot is going to be m sub j r sub j dot dotted into r sub j minus L, which is minus 1/2 sum over m sub j r sub j dot squared minus u equals a constant. Okay. But what you'll see is this is r sub j dot squared, and this is the same thing with a 1/2 in front of it. So what we're ending up with is 1/2 sum over m sub j dot squared. Takes care of that, minus a negative u, so it's a plus u, r sub n. And what is that? That's t plus u. And we recognize that as the energy. So that conserved quantity that we had here in the variational calculus, just on general grounds, in the Lagrangian mechanics scheme of things, that is actually the conserved quantity we call the energy, the total mechanical energy. And later when we do conservation laws, we'll return to this. But for now, we have just the basic formulation. We have the Lagrangian, we have the equations of motion giving us Newton's laws, and we have this first integral here, this one right down here, giving us the conserved quantity, the energy. So this here is conservation of energy. Okay, like I said, this is just what we've already learned, and we got back these equations here. So that's not the actual strength of the Lagrangian method. It's the convincer. So you're now convinced that this is Newtonian mechanics. And in fact, this equation here is going to be our Newton's law. This one in the mechanical. I don't have it written up here right now, but yeah, in the Lagrangian scheme. So let's see. I think we have a good treatment of this. Okay, so we went from the variational calculus, principle of least action, just translated symbols, and found that we have Newton's laws of motion, and we even have conservation of energy. Okay. So that's for starters. And again, make sure you really see what this translation was, because we have all the pieces of this, all the ingredients, but you just have to go through it and recognize them all. Okay, let's see how we're doing time-wise. This is right at the start. Well, start is longer than you think. Okay. So now we're going to use the Lagrangian scheme to do mechanics and solve some problems, set up some problems. So now we'll just title this Lagrangian mechanics. And the advantage of it is in the principle itself. So now that we know what these ingredients mean, I'll just always write this here as a shorthand. And the advantage of having a principle like this is that we're dealing with a scalar. So the Lagrangian kinetic minus potential energy is a scalar, and as such, it's going to mean the same thing regardless of what coordinate system we use. Right now we're just starting out with Cartesian coordinates and a bunch of isolated point masses and point mechanics. But since the principle involves the difference between kinetic and potential energies, any set of coordinates that we can use to formulate the difference between kinetic and potential energies is good. And the minimization principle will always give us these equations of motion, which, yeah, let's write here as well so we always have them in front of us. So will always give us these equations of motion. So the first thing we have to do is start discussing other coordinate systems. Okay. If all we had is Cartesian coordinates, then we wouldn't have had to set this up at all. So dl r sub I dot, once again. So you really get to know these equations here. So because it's a scalar, L is a scalar, we can transform to any set of coordinates and retain the form of Lagrange's equations. We can transform any set of coordinates and retain the form of Lagrange's equations. Remember the form of Lagrange's equations we got when we were just talking about any old coordinates. We weren't even talking about physics, right? So we're going to retain the form of the equations of motion, and that is a huge benefit when even trying to set up the equations of motion. Now, then I have to introduce a couple of concepts. So the next thing we're going to talk about is generalized coordinates. Generalized coordinates. And we'll take a set of q sub I equals 1 to n. So the generalized coordinates are any quantities that suffice to determine the position of the mechanical system. Any set of quantities that allows you to determine the position of the mechanical system. So it doesn't have to just be Cartesian coordinates. It could be a mix of Cartesian coordinates, angular coordinates, and so forth. So any set of coordinates. And we're going to require that they be independent, that characterize the position of the mechanical system. you can have a bicycle, for instance, and then each wheel would have an angle. It would be a different angle for the handlebars. Okay. And the whole thing would transform to some positions in Cartesian space as well. But bicycle a little complicated. We'll start out with things like the pendulum. Characterize the position of mechanics. So everything's important here. The fact that these coordinates are independent and that they simply specify the position. I'll start drawing a couple of examples. And these will be examples of problems that we then go ahead and solve. Okay, so let's see. Example. Let's start with the pendulum, M and L. This one's interesting because it's in two space, right? A plane pendulum's in two space in the plane, but coordinates x and y that you could attach to this are not independent. So if we try to set up a Lagrangian for this thing, x and y, we'll actually violate the conditions that allowed us to get those equations of motion. Okay. So a generalized coordinate, so I'll just write here, x, y are not independent. So here what we would do is choose the angle, and it would turn out there's only 1 degree of freedom on this. Okay. So choose the angle phi as the generalized coordinate. Okay. So that we feel at home with that, right? That's nothing new. Another example is if we were to have a block on a frictionless track. Okay, so here is our x-axis. There's a block on a frictionless track, and we're hanging a pendulum here, lowercase m, length L. So now this pendulum can swing, and it would have had these 2 degrees of freedom. It would have been swinging in 2 space, but m here is allowed to slide back and forth as well. Okay. So what we can now do is say our generalized coordinates are 1 Cartesian coordinate for this block, and then this angle coordinate for the pendulum. So they're independent, they're generalized coordinates. And the thing about this generalized coordinate is it's going to depend on x and y initially until you do the transformation from, and which we've of course done before, the transformation from Cartesian to angular coordinates. So this is a nice example as well. I'll just put some text in here. Block slides without friction. Friction. So then we have our generalized coordinates would be x and phi, and x could be a position on the x-axis there. Okay, so this is an example where you can mix up Cartesian coordinates and angular coordinates in a way we haven't done before. So this will be a system that we actually deal with later on in the semester. So you have to make sure they're independent. You've got these generalized coordinates. The traditional name are Q. So once again, generalized coordinates. It's the set of Q sub I equals 1 to n. And then this n represents the number of degrees of freedom, independent degrees of freedom. Okay. Then we have generalized velocity, and that is just the set of qi dot dqi dt. And with the set of generalized coordinates and generalized velocities, we now have to be able to put together our Lagrangian. Now the Lagrangian t minus u just falls into our lap when we're in Cartesian coordinates, but when we are in generalized coordinates, we're going to have to do a construction to find out what its form really is. Okay. Because we have to get the kinetic and potential energies in terms of these generalized coordinates. Good, but we can do that. So we've got generalized coordinates, generalized velocities. So the next task, construct L equals, it's t minus u of course, but it's L of q1 to qn, q1 dot to qn dot, and t. This semester we won't really be doing explicit time, but that's in there as well. Could be some really interesting problems with explicit time. Conserved quantity, systems with conserved energy don't have t in there, as we'll see later. But actually we've already seen it. We have the conservation of energy and it was lacking in explicit t, but we'll get back to that. So yeah, next task, we have to construct the Lagrangian with these new generalized coordinates that we have for the system. And you know, our plane polar coordinates, our cylindrical coordinates, our spherical polar coordinates, those are the most important generalized coordinates as well. The complicated mechanical systems can mix them up though and, you know, add various and assort it. Like this example with one Cartesian and one angular coordinate. But if you need examples of generalized coordinates, of course, just the spherical and planar and cylindrical ones that we're already used to. But yeah, next we have to construct the Lagrangian. And only then, when we have that Lagrangian constructed, and that's often, you know, half the task, you construct the Lagrangian and then you know your equations of motion are going to be correct. And then, of course, solving the equations of motion is always a difficult thing. Okay, how are we doing for time? I think we'll nail this thing here. Okay, so we're constructing the Lagrangian. Kinetic minus potential energy, and let's see where we start here. So U of I'll save that one for last. The potential energy transformation is just very direct. So transforming the kinetic energy is actually the real job. So transforming T, okay. So the idea is that we have, I'll give an example. Remember we had X was R cos phi, Y is R sine phi. Okay, so we've worked a lot with the plane polar coordinates. And X dot was R dot cos phi minus R sine phi. Phi dot, haven't done this for a while, right? Y dot was R dot sine phi plus R cos phi, phi dot. And what happened when we constructed X dot squared plus Y dot squared? Now t is equal to 1/2 m. We're talking about a single particle, right? And you'll remember x dot squared plus y dot squared, the cross terms went away. And we had r dot squared cosine squared plus sine squared, which is 1. And we had r squared phi dot squared cosine squared plus cosine squared was also 1. So we ended up with r dot squared plus r squared phi dot squared. Okay. So what we're going to do next is just do this in a general case for some general transformation. So this example we've done before, we're comfortable with. Now what about for a general transformation? So this was our x and y, and these are our q's. So we're looking at x sub I is equal to some function f sub I of q1 to qn. Okay, I equals 1 to n. That's what we're talking about. Plane polar coordinates, we have x sub 1 and x sub 2, q sub 1 and q sub 2. And what we had to do was take the derivatives and then square them and sum them. So that's our task in general. Okay. It's just like the plane polar coordinate transformation. So what do we have here for xi dot? Right. That's sum over, remember this is the chain rule, partial f sub I, partial q sub j. Okay, we have to choose a different letter. J equals 1 to n. So for each individual, partial f sub I, partial q sub j, and then q sub j dot. And apparently we have to take the sum of these objects squared. And then we'll have our kinetic energy. You know, we'll put the m's in there as well. Okay. So let's do that. Basically what we're doing is we're transforming from Cartesian coordinates to our generalized coordinates over here. And this I can erase everything here. Now, the kinetic energy T is 1/2 sum over m sub, I'll just write I for now, x sub I dot squared. So if we're talking about Cartesian coordinates, this would actually go from I equals 1 to 3 times n, right? We'd have 3 Cartesian coordinates per particle. But we're just going to use a generic I equals 1 to n for a number of degrees of freedom. Not worry about that. So this is what we have to do. And here's how we go about it. We've got a sum I equals 1 to n, m sub I. And now we're going to use different subscripts. And we have to square this. So we have the xi dot squared. So the way we're going to square this is the following. First I'll write df sub I dq sub j, q sub j dot, j equals 1 to n. And instead of just squaring it this way, which would just lead to trouble, I'm going to rewrite it with a different subscript. So d, it's still df sub I dq, but now dq sub k, q sub k dot. Okay. So these are identical quantities. Since I'm summing up j equals 1 to n, summing over all of those, and you can see the I here, and we're summing over the j and k. Okay, don't worry, this looks bad, but it's gonna turn out simple. Now, what we can do, since these are just finite sums, we can go ahead, 1/2 is still 1/2, right? We're going to do the summation j and k right here. And then what will be where we'll have sum over m sub I df dq sub j. This is I equals 1 to n df dq sub k, close parentheses, q sub j dot q sub k dot. Now I gotta consult the clock. Here I am at the punchline. Am I running out of time? We've got nothing but time. Okay. Yeah, I know. First time you see this, you're thinking, this is not good. Don't like where this is going. But it's not bad at all. In fact, I'm going to prove to you that this is just what we did up there. Okay. What's important here is that this big expression here, with sum over and all this, is a function of what? Okay. I's here all over the place. You know, since we're summing over I equals 1 to n, we're summing over all the i's, m sub I there. These functions f are functions of q1 to qn. So this thing gets another name. It's simply a sub jk of q1 to qn. What's important about this is that it is an n by n matrix, if you will, functions of the coordinates. Okay. And so the form of the kinetic energy, what we've arrived at, is this. I'll put this in a box. The kinetic energy has the generic form jk a sub jk of q. Right, I'll just say vector for all of those quantities. Q sub j dot q sub k dot. Now this is something that you see a lot of in math and physics. This kind of a double sum, so you get used to it. We're going to see them all over the place. It's called a quadratic form. Okay, when you have these you have these coefficients, these things right here. We'll see quadratic forms in different cases. If you've done linear algebra and matrix multiplication, things like that, you run into expressions like that. They're not uncommon at all. And our kinetic energy is a quadratic form, and these coefficients are functions of the coordinates, and these are the generalized velocities there. This is, like I said, a square matrix, if you want to look at it that way. So when we do theoretical work, we will often have this expression here. Okay. We won't have this big thing. On the other hand, when you construct the thing, you're automatically taking care of this. So my example is already on the board. For the plane polar coordinates, plane polar, Aij is a matrix. In fact, let's say it's of R and phi. That's our Q1 and Q2, okay? R and phi. It's a 2 by 2 matrix. And you know, if we were all together, I'd point to someone and have them fill in this 2 by 2 matrix. What is it? Okay, so we have R and phi. So we would have R dot, that's the R dot squared. And then we would have the R dot phi dot, the phi dot R dot, and the phi dot possibilities here. So we'll see that this square matrix here for this case must be diagonal. Okay. We have, for the upper entry here, we have M, and that's it. then we have zeros, and we have m r squared. So since I'm ending the lecture with this, and I would ask you just to make this clear to yourselves, okay? Just go through everything I've done here, and you can see that this complicated object for this 2x2 case that we did here, we did exactly this whole process. We did it for the 2x2, and if we were to ask what was the I, J, J, K, whatever, I'm using J and K here, let's be consistent, let's use J and K. And you know, Q sub 1 and Q sub 2 are in feet. Okay. See, in terms of a quadratic form, I feel like finishing this thought off. How many minutes are we doing here? Okay, yeah. Not that I think these lectures should always be a full 50 minutes, but this time looks like we're running up against that. Right, let me just complete this thought here. So this was an example of this process here. I'll put that up there on the board now. I want to just write this out. So if we were writing this thing out here, we would have t equals 1/2, and since it's this double sum, you can say we have a11 q1 dot squared plus a12 q1 q2 dots plus a21 q2 dot q1 dot okay, plus a sub 2 q2 dot squared. And now if we go to the polar coordinates one that I just erased, we have 1/2 m r dot squared plus nothing there plus nothing there plus m r squared v dot squared. Okay, I'm going to leave it at that. We've made great progress. We have the transformation of the kinetic energy. We'll use this a lot in our theoretical work. The potential energy is actually trivial, as it were. You just directly transform the Cartesians to the generalized coordinates and leave it at that. Okay, so yeah. So yeah, we'll have Lagrangian, general type of Lagrangian, using these generalized coordinates next time. Okay, good. So don't have any particular homework assignment for this thing, but as always, make some really good notes here, and you know, if you just work through this and really understood what we did, then it'll be a lot. Okay? Okay, see you guys next time.